Okay, welcome back. So as I was saying before, just as a reminder, tension's in our free body diagram, yes. However, it does not appear in our equation because tension is not a driving force, it's not a resistive force, it's just the force that connects the two objects together. So now that we have this information, we can go ahead and do our calculations for each of these values. So force Gx, so it's mass times gravity. I'm going to go with 10, and it's going to be sine 40. Hope I don't make an error here. Force due to friction. Oops, I already did. On the first, it's 60, because I want object B. Sine 60 minus force due to friction. So it'd be mu 0.3 multiplied by mass of the object, 30, multiplied by gravity, 10, minus force due to friction on A. So I'll start down here, 0.2, mass is 20, gravity again is 10, minus FGX, so it would be your mass, 20 times gravity, multiplied by sine 40, and that's equal to mass of the system, 20 plus 30, and I'm looking for the acceleration of the system. That's why I put the S there. So now we go ahead and do our calculations. And you'll be realizing, some of you will be realizing anyway, looking back at your formula sheet, you'll be wondering, where does angles go? I did forget to put on this cos 60 for my normal force, because remember the normal is perpendicular to the surface. So it's only getting a certain component of that. And similar here, this one should have a cos 40 as well on the two normal forces. So my mistake. So there is our resulting numbers. So I end up with 55.6 equals 50 A of the system, or acceleration of the system. So the acceleration of the system then, dividing that by 50, I get about 1.11 or 1.1 meters per second squared, and it is correct, our direction's clockwise. Now, if you got a negative force or negative acceleration, that means you guessed wrong at the motion. And what you would have to do is you'd have to switch the motion around and rearrange the equation and recalculate, because your forces of friction would then change direction. So keep that in mind. All right. So how do you finish this up then? Well, I'm going to make a couple of notes here. So you may want to hopefully have a little bit of space left. So I'm going to do this in red because this is the important part. So tension is easier to calculate with the driving object. I'll put that in quotations. So whatever is driving the system to move is how you calculate it. So that being said, you would take the tension in the rope. It's equal to the mass of the driving object. For us, it was B, multiplied by acceleration in the system. So our tension would have been 30 multiplied by 1.1, which gives us 33 newtons. All right, 33 newtons in tension. Now, if you decided that you're going to go with the trailing object, okay, keep in mind, so I'm just going to put a bubble here. Okay, if we wanted to use object A, be careful with direction of acceleration. All right, and then you also have to use you have to use you have to balance it basically. So that's why it becomes a little bit more challenging. So the tension in the rope for object A, so just doing the calculation in another direction here, the tension in object A is going to be tension minus F unbalanced equals mass times acceleration of the system. All right, so that's how you would calculate your tension, or tension is equal to mass times acceleration of the system plus the unbalanced force. What you need to remember is that A is going to be negative because it's moving up the slope. All right. So A is negative because object A is moving up the slope. All right. So when you go to do that calculation, so tension equals mass of the object is 20 multiplied by negative 1.1 plus our unbalanced force, which was the 55.6. So if you calculate that out, then we get 20 times negative 1.1. And then if we add the 55.6, we get 33.6 or 34 newtons, so 33.6 newtons. So you get the same answer. And remember, tension is uniform throughout a rope. So my last note then, tension is uniform throughout a rope. So the tension is not going to change depending where you are in the rope. Okay, if it's one segment, one rope, so this rope up here, so where's my magic pen? This rope, the tension is going to be the same no matter whether you're looking at the rope on that side of the pulley or that side of the pulley. The tension is the same throughout. So a rope distributes the tension evenly throughout. So there's your upper end question that you're looking at today. If you're gonna, yes, you can always use the leading object to determine your tension. I just wanted to show you because I always get asked, well, what happens if I don't have the information? What happens if I want to use the trailing object? Well, it still works the exact same way. So in your handout or in your package there's the homework from the textbook. The answers in the book are incorrect, and it gave me some headache there for quite a while because I thought I didn't know what I was attempting to teach here. However, upon further review and consultation to make sure I wasn't crazy, even though some of you will disagree with that assessment anyway, is that the textbook was calculating incorrect answers. So I'm not sure what they were actually calculating, but now I have given you the correct answers so that you will be a little bit happier when you go to check them. So I'm just putting in the correct units, but anyway, or vector notation. So there you go. So there is the homework. If you have any questions, we'll definitely clear them up in class. And good luck with this particular topic.